when it comes to the kidneys and the different components of the tubule portion, the nephron loop is really essential to the creation of an osmotic gradient. And when it comes to the nephron loop, that nephron loop must be coming from a juxtamedullary nephron. Remember that those type of nephrons have a very long nephron loop. It extends very far into the medulla of that kidney, and that provides multiple opportunities for establishing a gradient as we transition from one region of the kidney to the other. So in thinking about the countercurrent multiplier, just thinking about the name in and of itself, the countercurrent multiplier system is really about the interaction of the filtrate, so the content that we find within the tubules that are specifically within the nephron loop portion. So it's the interaction between the filtrate and the interstitial fluid. Now for countercurrent, that simply means that we're moving in opposite directions, and we're focusing on these parallel portions of the nephron loop. So there's an opposite direction of fluid flow through these adjacent or nearby sections of the nephron loop. Now, the multiplier is going to multiply, so it's going to increase the effect through going through this process. Now, the fact that the descending and ascending limb are so close to one another is important because it allows for the ability to their behavior to exert an influence on each other. So they can influence one another as a result of how close they are, and that influence is going to impact solute movement as well as water movement. And what moves is going to depend on where in the nephron loop we are, because there is a variation with the cell type that is seen between the thin descending limb and the thick ascending limb, which we talked about in the earlier portion. So the thick ascending limb is where your book starts. That's where we will begin. And remember that the thick ascending limb has mitochondria. There's a ton of active movement here. And so the active transport that's occurring is the pumping out of salt. And that salt is going to head into the interstitial fluid. So we are able to move salt out of the tubule. We have a ton of mitochondria, so we have a ton of ATP, which is going to help drive this active transport of solutes against their gradient. Now, remember that the thick ascending limb is not going to be permeable to water, and that's going to be due to the low concentration of aquaporins that's seen in this portion of the renal tubule. So we have our thick ascending limb pumping salt out. So we are increasing the solute concentration that is seen within the interstitial fluid. So if both sides are able to exert an influence on one another, the thick ascending limb behavior is going to raise solute concentration out here. Now the thin descending limb is not permeable to solutes, but it does have the ability to allow for the movement of water. And so there will be aquaporins that are found on the thin descending limb. And so the thin descending limb is going to say, my surrounding environment, my interstitial fluid has a ton of solutes out here. So in order to counteract that, I can't allow for diffusion down my gradient of the solutes in because they're not permeable, but I can achieve water movement out with a possible goal of reaching equilibrium. That doesn't occur, but it's something that it has a tendency to do because there is a desire to reach equal solute concentrations on either side of that membrane. So we will, in response to sodium chloride ions being pumped out on this side, be able to draw water out through those aquaporins found on the thin descending limb. So there will be movement that is driven through properties related to osmosis, and that will continuously drive water out of the descending limb. Now we can imagine that if we're moving water out of the descending limb, then what we're doing is changing the amount of solute that's present per volume. So that's going to have an impact on the concentration of solute that is left behind. So this is part 1 and 2. In the next slide, we'll go through the remaining portions of the multiplier system. So as stated in the previous portion of this countercurrent multiplier, we have had loss of water through being drawn out via osmosis from the thin descending limb. Now, because we're driving water out of the tubule on the descending side, we're going to increase the concentration of salt that is found within the filtrate in this region. And so as we progress towards the bottom of the loop, we're going to see that concentration continue to rise. So the impact of water leaving the descending limb is an increase in solute concentration of the filtrate. Now, with this continued water's loss and this rise in solute that's found over here, we're going to be able to maintain a high solute concentration that can be used by the ascending limb. So we're drawing water out, and as we draw water out and work our way down, we're seeing an increase in the concentration of the filtrate with respect to salt. And this is going to provide the solutes that are used to be pumped out as we head up the thick ascending limb. So this is what allows the process to continue to loop over and over. So this creates a gradient that is going to serve as a positive feedback loop. So here you have it in summary. I'm just going to reiterate it in a slightly different way. So you have a higher osmolarity. Okay, so the higher the osmolarity that's seen in the interstitial fluid, the more water will leave the descending limb through osmosis. So there's a relationship between the concentration in the interstitial fluid versus the concentration inside of the tube. The more water that leaves, the higher the solute concentration that remains in the tubule. The more salt in the tubule, the more salt that is available to pump out of the tube here and into the interstitial fluid as we work our way upwards. The more salt that is pumped out of the tubule and into the interstitial fluid, the saltier the interstitial fluid becomes. And so again, these events are helping to perpetuate this cycle. When it comes to this particular image, this one came from your Campbell book as a way of explaining generating a osmolarity gradient within the kidney. But what I want to focus on in it is what's taking place here, which is the process of urea recycling and the medullary osmotic gradient. So when we discuss urea initially, we discuss it as a metabolic waste product, something that we want to get rid of. But because water conservation is really important to the kidneys, urea is actually involved in helping to form the medullary gradient. When it comes to this process, urea is going to enter the filtrate in the ascending limb of the nephron loop, and that process takes place through facilitated diffusion. Now, as the filtrate moves on, the collecting duct on the cortical side is going to reabsorb water, but it's going to leave that urea behind. So urea is going to stay within the collecting duct. Now, as the filtrate heads downwards, then we're going now into the medullary region, and we have highly concentrated urea there, and that concentrated urea is going to exit out. Okay, so now that we're in the deeper region, so in the medullary region, now urea leaves. So urea leaves out into the interstitial fluid of the medulla, and this forms a pool of urea, and that urea is going to get recycled back into the ascending thin limb of the nephron loop, and then that process happens again. So in this way, we have urea that is contributing to the high osmolarity that we see down here. So obviously, it's not the only thing contributing. We've discussed how the countercurrent multiplier helps to accomplish that, but I also want to address the role that urea can play in this process as well. So what would happen if we were dehydrated? So if we were dehydrated, then urine would end up being more concentrated. And so we'll go through that process here. So dehydration can be associated with high blood osmolarity. And so the goal then would be to stimulate the release of ADH. And ADH can help to promote that water reabsorption. Okay, so here we have filtrate that's entering into the collecting duct. And at this point, there's not going to be an osmotic gradient at this portion or this region because we're not very deep into the kidney here. And so there's not going to be any extensive movement of water. Okay, now, again, when it comes to the ability to form concentrated urine, we are depending on the presence of hormones. Okay, so we're going to utilize ADH, and ADH will lead to the upregulation of aquaporins, which will allow for movement of water from out of the filtrate into the interstitial fluid. But at this point, there's no gradient that would drive movement. So right now, there's no water that's being reabsorbed. Now, if we add in the increased concentration of the interstitial fluid compared to the filtrate concentration with the presence of ADH, then this is going to create a movement of water out of the filtrate and into the interstitial fluid. So we are able to accomplish an increase in the concentration of solutes within the filtrate by allowing water to leave. So as we progress further into the medulla, the concentration of the interstitial fluid rises, which means water reabsorption is going to keep on happening as we work our way further and further down. We're heading towards the papillary duct. We know from there that we'll have convergence, we'll have our urine kind of outlet as far as our calyces are concerned. And by the time we're ready to exit out as urine, we're going to have a highly concentrated amount of fluid. Now, the fact that we are also continuously removing water from this process also indicates that the amount of urine that we're going to be releasing will be relatively low. So we'll have kind of a scanty amount of urine that's released, but it will be much more concentrated. And this is because we are able to utilize aquaporins, and that's due to the presence of ADH in conjunction with the established gradient. So if we didn't have this gradient, then we couldn't depend on it to drive continuous water release or removal from that collecting duct as we progress further into the kidney. And so the ability to generate this multiplier works hand in hand with its maintenance and preservation. And so the countercurrent exchange is what allows for preservation of the gradient that was established by the countercurrent multiplier. So something that I often say in going over these two concepts is that you don't want to use their titles interchangeably. We're talking about different things. They're both essential for the osmotic gradient, but how they are essential, the role that they're playing is not the same. So when it comes to the countercurrent exchange, we also have opposite movement. And so what we're focusing on now when we say countercurrent is the direction of blood flow. So we can see that the direction is opposite. And we're focusing on the type of capillary that is found along the nephron loops. So the countercurrent exchange is about the communication that takes place between the nephron loop and the vasa recta. Now, as plasma found within the vasa recta makes its way down, the concentration gradient is going to favor movement of solute into the vasa recta and water out, because as we head further into the medulla, the concentration rises. Now, when it comes to permeability, the vasa recta is permeable to the movement of solutes as well as water. So it's not the same relationship as what was seen within the nephron loop, descending and ascending side. So again, as the plasma works its way towards the medulla, it enters a region that is increasing with respect to concentration. And so in response to that concentration, there can be movement of those solutes down their gradient, movement of water out into the surrounding fluid, both trying to achieve the same thing, which is kind of as equal of a concentration on either side as possible. Now, as the vasa recta begins to turn upwards, the solute's going to start to unload, because as we head further up, the concentration is going to decline. So as it turns back upwards, the solute begins to unload from the plasma into the interstitial fluid, and the vasa recta will also take some water back in and end up carrying some of that water away to be absorbed by the kidney. And this process does not impact the osmolarity of the medulla. So this process is what allows for a very minimal solute to be carried out of or into circulation. So the fact that we are initially pulling some solutes in, but then letting them back out before this flow of fluid leaves the kidney allows for maintenance of the osmotic gradient. So the purpose of the vasa recta is to work hand in hand with the nephron loop, and it's in order to ensure that the gradient is not perturbed, that we are able to still maintain this relationship as we work our way from the cortex to the medulla in increasing osmolarity. So if the vasa recta is not able to establish this relationship of picking up some solutes and then releasing them before that fluid exits out, then we would expect for the osmolarity gradient to be dissipated, to essentially diffuse away once generated by the countercurrent multiplier. So the time that's invested in establishing the osmotic gradient and maintaining the osmotic gradient is just so that the body can later fine-tune the concentration when needed. In this image, we're looking at the process of producing dilute urine. And when it comes to fine-tuning, this is going to require utilization of facultative reabsorption, which means that hormones will be involved. So in this scenario, imagine that we are overhydrated, and in response to this overhydration, the production of ADH will decrease or be completely gone. And when it comes to ADH and its role at the collecting tube or collecting duct is that it helps to reabsorb water. So if there is no ADH, then we're not going to have any reclaiming of water back into blood. We're going to allow it to remain within the filtrate, and it's going to go ahead and pass out of the body. Now, something to keep in mind is that in conjunction with the ability to hold on to water as it works its way out through the nephron and towards the collecting system, is that we're still able to take back our solutes. So solutes can still be exiting out of the collecting duct, but water is not going to head out. And the reason why it will not be heading out is because there is no aquaporins, and essentially aquaporins is what makes this region permeable to the movement of water. So we depend on aquaporins here. So ADH is controlling that. So no ADH, no aquaporins, no movement of water out of the filtrate. It stays. There's still movement of solutes, and that's going to further lower the kind of osmolarity value that we would expect to see as we work our way through the collecting duct. So this is what will create that dilute urine. When it comes to these numbers, I'm not going to expect you to know the specific numbers, but just knowing how things transition as we go through the nephron is important. So when it comes to the filtrate and the surrounding environment, it starts off in an isoosmotic fashion, which means that there's nothing that's really driving movement in one direction over another. But notice that as we head into the nephron loop, the filtrate is becoming more concentrated, and this is due to the behavior at that thin descending limb. The ability to move water out will progressively increase the concentration of the filtrate. And then we get to the bottom, that's our most concentrated area. And as we work our way up, we have that active transport of solutes out of the filtrate, which is going to start to decrease the solute concentration of the filtrate. And so we'll see this continual decrease as we move those salts out. And then we can still have reabsorption taking place along the distal tubule and the collecting duct. So the key thing for the production of dilute urine is the role that ADH will play. And by role, I mean its inability to lead to aquaporin insertion along the membrane because it's no longer present, or is present in such low amounts that any type of water movement here would be relatively negligible. So if we're producing dilute urine, there should be a correlation to dilute urine in an absence of ADH. So in this slide,